Hello, and thanks for joining me today. We're going to be going through the Module 2 case study for the TransportHealth R package. I'll show you how to use Module 2, which uses g-computation to conduct transportability analysis in R. Before we get into the actual coding, I just wanted to remind you of the many steps that go into conducting a transportability analysis. As you can see, first, our transportability analysis really should be grounded in stakeholder engagement. We need to find the right data sets, and then we need to curate our data and make sure they're harmonized. We're going to be skipping over those steps in this example and assuming that they have already been completed. Instead, we're going to focus just on this component, actually conducting the analysis in R once we have our data curated. As I mentioned before, we're going to go through an illustrative case study on transportability analysis using g-computation. While g-computation is not the most popular approach for conducting transportability analysis, its popularity is increasing, as you can see here in our graph showing the applied transportability and generalizability analyses in the published literature over time. G-computation is increasing in popularity partly because it can be conducted without merging data. What that means is that it's a better approach if you have restrictions that do not allow data to be transferred from one data holder to another. In terms of data requirements, g-computation requires individual level data in the source population as well as individual level data in the target population, just like the weighting approaches that we covered in Module 1. So let's contextualize our case study and understand what we're trying to estimate. So in this case study, we are interested in the effects of an antihypertensive medication, that's our treatment, on systolic blood pressure, our outcome, in comparison to standard of care in our local population. We have two data sets. The first is individual level data from an observational study conducted in the US, which includes information on the treatment each patient receives, their systolic blood pressure, and some other individual characteristics that might be related to blood pressure or treatment outcome. In addition, we have routinely collected individual level patient data from our local population that includes those same characteristics, but does not include information on the treatment received or blood pressure. Our aim is to estimate the effects of treatment on systolic blood pressure in our local population. Here you can see a directed acyclic graph or DAG of our causal problem. In this analysis, we want to control for confounding, and then we want to adjust for effect modifiers. Through our stakeholder engagement for this hypothetical example, we identified the following covariates to be adjusted for confounding: sex, percent body fat, and stress level. In addition, the effect modifiers that we want to adjust for are stress level and aspirin usage. So you can see here that in our example, stress level is both a confounder and an effect modifier. This table presents an overview of our two data sets and the variables they contain. You can see that in our study data set, which is our source data from the US study, we have 6 different variables. We have our covariates and effect modifiers, as well as our treatment and outcome variables. In contrast, in the target data set, which is our data from the local population, we only have 4 variables. These are our covariates and our effect modifiers. Now we'll jump into the actual R code. Our first step will be to load in the TransportHealth R package. Here we've placed the names of the variables and how they're coded at the top for reference. And then our two data sets. For this analysis, we'll be using one data set called study.csv and another called target.csv. I've saved these both in my R project folder just to make it easy to read them in. So I'll read in both data sets. Then I'm going to make all of our binary values factors. Here I've made a nice little function to speed up the process, but you could do it manually for each of the variables in your data set if you prefer. We need to do this for both the source data set and the target data set. Now we're going to look at our target data set and confirm that we don't have any treatment or response data in the target data set. And we're going to review our source data set as well and make sure that our variables match and we do have a response and treatment variable there. Now that we've confirmed that we have the right data sets, we can perform our transportability analysis using g-computation with two separate functions, transport-GC prepared model and transport-GC. The arguments for the transport-GC model function include an outcome model. You need to specify the treatment, the family or the type of outcome model to be fit. We need to specify the study data, and in this case, for the outcome model, that will be the source data. And lastly, if we have privacy considerations at play, we can wipe the source data from the resulting prepared model object. To transport the outcome model to our target data, we'll use the transport GC function, which has three arguments: effect type, where we indicate the type of effect that we'll be transporting, such as mean difference or risk ratio. Then prepared model, so this is the name of the object returned by the previous function, as well as the target data set. Our first step is to fit a regression model of the outcome in terms of the covariates and effect modifiers. This step will only use the source data, study data. You can see we've entered our arguments as specified above, including our outcome model, our treatment, the treatment levels, the type of model we'll be conducting, as well as the study data source, and that we don't want to wipe the data from our model object. Then we will use this model to estimate the average treatment effect in the target population. We will use the transport GC function and save the results as object of result. As you can see, we've entered the arguments that we talked about above. Here we'll be transporting a mean difference, and we'll be specifying our target data called target data. We can view our results using the base summary function. Here we can see the general model that we fit, as well as the family, the study data, and we confirm that our data was actually wiped or not from the model. We can see the different estimates and coefficients as well. We can use the base plot function to create a plot showing the transported effect estimate with 95% confidence intervals. Lastly, we might want to examine the residuals of the outcome model to assess model appropriateness. The lack of pattern observed in this plot suggests the model is appropriate for our data.